Welcome. Today's lesson is entitled Law of Cosines and Area of Triangles. And so as you can see on your notes worksheet here, what we're going to do is just start out with one more formula for the area of a triangle. And then what we'll do is, in just one spot on your notes worksheet, really have all the formulas that we've been playing around with non-right triangle trig. And then we'll just do one more review problem using law of cosines and kind of wrap it up and sort of have a culminating piece to the non-right triangle trigonometry. So anyway, let's get started right away. This one is called Heron's formula for the area of a triangle. And everyone, if you would, maybe just underline that piece. This is when we have the three sides of a triangle, so SSS as a result. And if you're interested, I do have a proof, I'm sure, somewhere lying around. It does use the law of cosines to develop it, so that's why it's kind of taught in this particular section. So anyway, area of a triangle is really based on a big square root here, so if you can get that going on your paper, that would be great. And you will, of course, see an S value emerge, so I will define what S is momentarily, but it's really a product of four values: S, S minus A, S minus B, and S minus C, all underneath the root there, so let's be very clear about that piece. So A, B, and C, of course, represent the lengths of the three sides of the triangle, and S, as it says over here, is what is called the semi-perimeter. So if you can write that in there for me. Really, again, just semi would be half, so half the perimeter. And that's what we'll just kind of jot down here, and we'll do a couple problems. We won't call it an official example, I guess, but it looks like I have a grid kind of laid out on your paper here. And what I figured we would do is just draw a couple triangles with it, maybe throw some lengths of sides on there, maybe do a little estimating, and then actually go ahead and calculate that area as a result. So why don't we do two? I think that should be satisfactory for something along these lines right here, and see where it leads. So how about this, everyone? Let's get this going. If you would, how about just somewhere down in the lower left here, just put a little point if you would. Anywhere right in there would do. And let's navigate off that point if we can. So here's what I'm thinking, everyone. If you would, from this point, can you guys go 3 units to the right, and then go, how about 4 units up? 1, 2, 3, 4, and then put a point, something like that. So from here, guys, 3 right, 4 up, put a point. Okay, I'm just kind of thinking about where I want this next piece. Okay, everyone, how about this? Now, from this second point, can you guys go 2 units left, 2 units up, and put another point? Something like that would do. And when you get an opportunity, this will, of course, be the 3 vertices on our triangle. It'd be great if we had a ruler here, but oh well. Let's go ahead and kind of sketch that in place right there. Okay, so that would represent our triangle that we will find the area for. And what we're looking for, of course, is the number of square units inside this triangle. Now, my grid's not perfectly square, by the way, but I think it still should suffice. So how many square units? That's what we're looking for, the space inside this triangle right here. And this formula allows us to use 1, 2, 3 sides in order for us to get it. So just to get this moving along a little bit, I'll help you label the 3 sides, and then we'll do a couple things with it. So actually, I'm going to use a little right triangle trig. Well, actually, no, I'm going to just use the Pythagorean theorem. I guess that's the way to do this. So I'm going to go 3 and 4. If 3 squared and 4 squared, everybody, would give me 25. Square root of 25 is 5. So as a matter of fact, this should be 5 units from there to there. Okay, good. Now here, everyone, I went 2 over and 2 up. So 2 squared and 2 squared would be 8. So this is going to be the square root of 8. I know this decimal. It's about 2.83, give or take. So from there to there, if I had it all right, it should be about 2.83 units. Okay, so I've labeled 2 sides. I'm going to label the third for you as well, trying to find this piece right here. And I see it as sort of the diagonal to this. So 1 over, and then 1, 2, 3, 4, 5, 6 down. So 1 squared and 6 squared. 1 squared plus 6 squared would be 37. Square root of 37. This one I'll bring my calculator up just momentarily. And just to make sure I have that piece, square root of 37 is, alrighty, perfect, 6.08. So again, it's not going to be perfect, but I think for our purposes, I think it's fine. Okay, everyone, here's what I'm going to ask us to do. We'll do kind of a 1 and a 2. So everyone over here, let's kind of highlight this piece. Put a little 1 right off to the side right here, and let's do a little work on this. So number 1, everyone, if you would, can you write the word estimation? Or estimate, how about that? And I guess I would ask you, and I'm going to do mine, of course, but you do yours. Try to count up the number of square units inside here. Obviously, we have parts of the square units and so forth, and you have a couple full squares. So here's 1 and 2, almost fully a third. You know, and what I'd ask you to do is try to count up the square units inside our triangle, and that, of course, would represent our area. And so I'm going to come up with an estimation momentarily. I'd ask you to pause the video for just a sec and come up with yours. I'm going to guess, and just speculating here, I'm going to guess about 7.5 square units. That's going to be my guess. Nothing special about it by any means. Just taking a very brief look, at the triangle and coming up with that. So I'm saying it's about 7.5 square units. Now let's find out. So everyone, the first order of business with using Heron's formula is we have to find S. So everyone, if you would, S would be half the perimeter. So the perimeter would be adding up all the sides, and I would just divide that in 2. So in this case, just working our way around, the first one was 5. Second one was, 2.83. Sorry about that decimal there. Let's get rid of that. So 2.83. And then the third one I saw was 6.08. Everybody, we take that and we divide it by 2. Okay, perfect. So let's grab the calculator, everyone. I'm going to do this as well. You do it with me. And let's go ahead and find that semi-perimeter. So, let's bring that up one more time. There we go. And so I have 5 plus 2.83 and then plus 6.08. Everybody add up the 3 sides, get the perimeter, and now divide it by 2. Okay, so my half perimeter would be 6. Make sure I have that, 6.955. All right, that's absolutely perfect. Now the nice thing about this formula and the way this is going to work mathematically is when I take my S and then S minus A, S minus B, and S minus C, all of these values will be positive. And then we should end up getting just the product of those underneath the root, and now we should be able to get our area. Watch the units unfold, by the way, as we go through the process too. So anyway, let's go for it. Everyone, if you would, give me a big area. And I'm going to go ahead and write this first. So it's 6.955, and then times 6.955 minus S. I'm sorry, minus 5, excuse me. Couldn't even read my own handwriting there for a sec. So minus A, which is 5 units. Then minus B, which is 2.83 units. And then, sorry, I'm going to have to tuck this down here. And then also times S minus C, which is 6.08 units. All of that underneath the root, guys. And we'll type that in momentarily. Okay, so that's just our formula right there. Now, before we do the calculation, just sort of interesting to note in terms of the units, think about this, everybody. Say I was in centimeters, just for argument's sake. This would be centimeters times centimeters times centimeters times centimeters. So 4 different linear measurements. I'm just saying centimeters there. And if I did centimeters times itself 4 times over, that would be centimeters to the 4th. Now, everybody, obviously we know area is not in units raised to the 4th. So take a look. Now, everyone, I apply the square root. I'm going to apply the square root numerically, and I would also apply the square root on the units. What is the square root of centimeters raised to the 4th? Well, guys, of course, it would be centimeters squared. Or in our case, since we don't have this as centimeters, just our linear units squared. And so it turns out working out perfectly in terms of our area units. Okay, well, guys, let's go ahead and get that number. So here we go. Oh, I did that again. Interesting. So here's what I have. Square root. And let's go for it. So I have 6.955. And then I just let it run, guys. Just 6.955 minus 5. And then same 6.955 minus 2.83. And last one here, parentheses, 6.955 minus, what did we say, 6.08. Excellent. I hit enter, and that's what I end up getting. Just over 7 square units there. So let's put that in. Area is 7.005 square units. I'll box that up. Nice and looking good. Okay, so we did an estimation. Mine was 7.5, not too far off by any means. And we used the S value and plugged that in. Let's do one more as we have the time here. So let's come over on this side of the board. And let's find a spot, I don't know, just kind of thinking out loud with this. How about right in there? Again, a little lower, and then I'll work from there. Okay, everyone, how about this? From this point, go 1, 2, 3, 4, 5, 6 units to the right and 2 units up. And put a point for me. 6 right and 2 up. Okay, now, from here, guys, how about we go, let's see, how about 7 up, 1, 2, 3, 4, 5, 6, 7, and 3 to the right. Let's do that. So 7 up and 3 to the right. Not bad. I kind of like that piece. A little bigger. Make it a little more challenging in terms of our estimation here. So I have that, and then there we go. Looking good. All right. So there is my triangle, as you can see, a little bigger. I'm going to go ahead and help you with the 3 sides first, and then we will run our estimation and our calculation across as well. All right, here we go, everyone. So first order of business, it looks like I went 1, 2, 3, 4, 5, 6, and then up 2. So 6 squared and 2 squared, everybody, would give me 40. And I know square root of 40. It's about 6.32-ish, somewhere in there. I've got that one down. Okay, so about 6.32. Everyone put that in if you would. Now this one, what did I eventually say? 2, 4, 6, 7, and 3. So 7 squared is 49. 3 squared is 9. 49 and 9 make root 58. Let me bring the calculator up there for a sec. Square root 58. Okay, and I've got 7.62, give or take, somewhere in there. Excellent, 7.62. Now what did it turn out to be here, just out of curiosity? 1, 2, 3 over, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, yikes. So 9 squared is 81. 3 squared is 9. I have 81 and 9, everybody, which is 90. I'm going to need square root of 90 on that. So let's get that going. I'll just give you this piece. Again, don't worry about bringing up your calculator. Looks like I get about 9.49. Okay, so again, it's not going to be perfect because I'm rounding my decimals here. But for our purposes, I think it's more than adequate. So guys, what do you say? Put a big 2 right there. And I'll write the word estimate. What do you think? Ooh, a lot of them. So start counting up there. I'm going to just think about it for a sec. It'd be great for you to pause the video for a moment and count them up. What do you think? How many square units are inside that triangle right there? All right, I'm going to go with about 22. And that is a quick guess on this, so we'll see how I did. But maybe you have something that'll be a little better. I don't know. I'm not sure. We'll find out how good mine is momentarily, and we'll see how close yours is. Okay, guys. Well, let's do a little S on this. So first and foremost, S is half the perimeter. So I add the 3 sides up. 1, 2, and 3. And divide by 2. So first order of business, of course, everybody, is to go ahead and get that semi-perimeter. Let's do that here. Grab your calculator. I'll grab mine. And let's see what we get. So 6.32, 7.62, and 9.49. There's your perimeter when I add them together. I divide by 2, and that's what I'm getting, everyone. So take a look at that. Make sure you agree with mine, and I've got about 11.715. All right, that would be the number of units, halfway around, so to speak. And now, guys, I'm going to have to run mine down here, but let's see if we can get this. Big square root, massive. And let's go for it. S minus A. And so I'll just start anywhere. It doesn't matter what A, B, and C would be. And sorry, I'm already running around out of room here, but let's see, 11.715 minus 7.62. And then, sorry, I'm going to have to come back down here as well. Not great. My apologies on that. 715 minus 9.49. Okay, here's your S. Here's your S minus A, S minus B, S minus C. Well, let's let the calculator do the work for us here. I'm going to bring this back over, and let's go for it. So I grab my calculator, big square root. Here's my S. Just type it in nice and easy. And then that number minus A, so minus 6.32. Close them. Same number, guys, 11.715. Minus the B, so minus, in my case, 7.62. One more time here, and I do 11.715, and then minus 9.49. Notice I let the calculator pretty much do it all at once there. I put square root initially, and that way I have my S, S minus A, S minus B, S minus C, all in place. Interesting. Rounding there, it looks like it's pretty much right at the 24 mark. So 24 square units. Excellent. All right, I'm going to box that up. And so we did 2 at this stage. Let's see, and I like the estimation piece just to really understand what does area mean. And in this case, my count was about 22 square units inside. Could have been better, could have been worse. The actual was right at 24, give or take. All right, if you have any questions on that particular formula, let me know. If you want to look in a little more detail on it, again, the proof uses law of cosines to pull it off. Okay. Well, as I said, I figured it would be good to get it on one notes worksheet, just all the non-right triangle trig. So it says review of formulas for oblique triangles, and let's go for it. So these you should know pretty well. I like the law of sines. It works out really well. Simple calculations, generally speaking. Just cross-multiplying. Sometimes we have issues with inverses, but hey, we deal with them. And there were 3 situations that we saw them, everybody. ASA, SAA, and then SSA. This was the one that was ambiguous, if you remember. So that was the one that we had to kind of deal with, not necessarily getting one definitive triangle. Here's why I have 2 blanks for the cosines. So law of cosines, this is pretty much the straightforward version. So b squared, c squared, 2bc, and then the cosine of the angle across from whatever's over here. Now the only reason I have the second one is sometimes this comes up is just if I'm trying to find the angle, you can go ahead and do an inverse cosine on this. I just play off this. I just remember this one and then solve the angle that way. But just if you want an alternative, you would kind of do an inverse cosine on a whole lot of stuff here. But as I said, this to me is totally up to you. If you want to learn this, memorize it, whatever the case may be. But that's essentially what it would be, the angle. I like personally just solving for A from this format right here. That's just me personally. But I wanted to at least give you that option. Okay, and let's see the 2 situations with this, SAS and SSS, of course. All right, wonderful. And now we have 2 areas of triangle formulas. So let's see, this was the one we did the other day. So 1/2 BC sine of A. So basically 2 sides and an angle in between. And so what that would mean is that's SAS. And now everybody, we have one more formula coming our way, herons. And S minus A, S minus B, S minus C. Please just make sure it is all underneath the square root. And that, of course, deals when you have 3 sides in the triangle, whatever they may be. So just trying to summarize as best as possible there the situations that we used it. And remember, in terms of this, the law of cosines was just to get us started. If we can use law of sines, obviously that is preferable. But we do have to be careful. We do need to make sure we do it correctly. So I have one example that we'll take a look at, just kind of a refresher here. It is as contrived as it gets. It's kind of silly in the fact that it's not applicable, in my opinion, at all. But I think the math is perfect for our discussions here. So let's go for it. Let's try it out. I think you have a diagram on the back that helps us out with this. So I'll be going page to page here, and we'll see what we can do. So in attempting to fly from Chicago to Louisville, a distance of 330 miles, a pilot inadvertently took a course that was 10 degrees in error, as indicated in the figure. Okay, so we'll get that figure momentarily. If the aircraft maintains an average speed of 220 miles per hour, and if the error in direction is discovered after 15 minutes, so after a quarter of an hour, what bearing should the pilot turn to head toward Louisville? Okay, well, let's see what this looks like here. All right, so here's the pilot where he wants to go, where he should have gone, and then goes 220 miles per hour for 15 minutes, so we'll have to figure out what this is right here. And then realized he made the error. Now what's the bearing from here to here? So just as a matter of fact, everyone, if you would, can you put a north-south line right in there? And I'm seeing this, as a matter of fact, as our bearing. Interesting. Which now, just thinking out loud with this, it looks like we will probably have to find that angle inside here. All right, well, let's see what we have, and let's see what we can use, and so forth. I have one side, 330 miles. I have the 10-degree error, so there's 10 degrees right in here, and that's it, unfortunately. I think there's some more information in the problem. I think he was saying something about, the problem was saying something about 220 miles per hour for 15 minutes. And so I think that's this piece right here. Let me just confirm that, and then maybe we can utilize it. There it is. So everyone, do you see that piece? So it was going 220 miles per hour after a quarter of an hour. So why don't we do this, everyone, just kind of thinking about getting that distance. How far did this pilot travel before realizing the error? So 220 miles per hour and went for a quarter hour. So let's just divide that by 4. Okay. So according to my calculation, everybody, it looks like the pilot went 55 miles. So that, everybody, is what you're going to put in right here. I think that is a necessary piece. And that's pretty much all we have. Now it's up to us. So take a look at the scenario that unfolds here, everybody. It looks like side, angle, side, which means really, to some extent, our hands are tied here. There's only one thing that we can get using this scenario, and that would be this right over here. I'm just going to throw a variable on it and go for it. So SAS really does lead us to one particular part, and that is the opposite side. So I'm going to go to my part A. I've got a couple things labeled, and let's go ahead and solve. Law of cosines, everybody. So here's how it works. I think it's x squared, and I have 330 squared, 55 squared, minus 2, 330, 55, cosine of 10 degrees. So we're going to take this right here, everybody, and then we're going to square root it and get an x value. So that third side in that triangle is unknown at this stage. Let's go find it. So everyone, type with me if you would, please. 330 squared, 55 squared, minus 2 times 330 times 55, and then times cosine 10. No, you know what? I know what happened there. Sorry. And you guys as well. Make sure you're in degree mode for this. So you know what? I'm going to re-enter that. Sorry about that. And let's see if it gives us something different. There we go. So realized just half a second too late there that I was in radian mode. Obviously, we are taking the cosine of 10 degrees on that. So I redid, and there's now in degree mode cosine of 10 degrees. And of course, everyone, let's go ahead and square root this. So square root of that answer. And there we have it, about 276. All right, close enough where we'll just go with 276. So on your paper, everyone, let's write that x is 276 miles. And I think we're going to need that, by the way. So 276 miles. Okay. Now, here is the scenario, and this is a good conversation to have at this point. We need this angle right in here, right? And my diagram sort of tells us what type of angle it is, but I would say we need to be careful on it because we don't know it's drawn to scale. In fact, it really doesn't look like it is. This is 55 compared to this 330. So I need to be very careful on assuming what type of angle this is right here, which means at this stage, guys, I'm in an SSA situation with my law of sines. So what I'm thinking is we have our 276 over the sine of 10 degrees, which is great. That's exactly what we wanted. I don't know that we want to get this angle just yet because I'm going to have to do an inverse sine on that, and as a result, the calculator will assume it's acute, and I don't know if it is or if it's not. So what I would say, and we wrote this on our paper the other day, is we should probably find the smaller angle first. And the smaller angle is going to be across from the 55 miles as opposed to the 330 miles. So I'm going to put this, since we're talking about two angles, I'm going to put that as an alpha, everybody. And I think, even though we don't necessarily need this up here, I think we need it to get this piece. So that's the way I'm thinking, and this is the review we talked about from just law of cosines, is if we're using law of sines, you want to find the smallest angle that's left. And so anyway, now I've got 55 sine of that angle. And so that's what I'm going to do. I'm going to grab my calculator here and move it on over just a touch for us, and let's go for it. So I am in the proper mode, which is smart. Let's see. So I want 55 sine 10 degrees, cross multiplying there, and then divide by the 276. Got that. There's my sine ratio for alpha. And again, I am confident that alpha is an acute angle because it is the smaller of the two left. And so it has to be acute. So I'm going to go ahead and do an inverse sine on that ratio, guys, and I end up getting, let's just round up to about 2 degrees. Okay, so everyone, 2 degrees right in there. So what I see is this first angle is 10 degrees. Everyone look at it with me there. And this is 2 degrees right there. Now, everybody, do we have this beta? I'll call it beta. Now we know it is obtuse, and that's 12 degrees total, and I still have to get to 180. So I think that has to be 168 degrees. And if we did law of sines on that, again, we probably could have figured out it was the obtuse one. I understand that. If we did law of sines and tried to get beta right away, it would have given us the reference angle, which looks to be 12 degrees, by the way. But that wouldn't have been this, and we would have been a little unclear about that. So by finding the smaller one first, then we know exactly what this has to be. All right, perfect. Let's go back. I think we need to find a bearing here. I'm hoping everyone's okay with these couple pieces. First of all, that's 90 degrees right in there, sort of flying directly east, so perpendicular with my north line right there. So there's 90 degrees. And if that's 90, I'm hoping everybody sees that that is 78 degrees right in there. Remember kind of talking about bearings, that would be 78 degrees, rotating off the north axis, and the terminal side is going in an easterly position. So that, everybody, is what I see as the bearing, which is exactly what Part A had originally wanted. So what bearing should the pilot turn to head toward Louisville? And I'm getting this right there. See if you are in agreement on that. So the whole angle was 168 degrees. Take away that 90 there, and I'm getting 78 left over, rotating off the north, going in an easterly direction. All right, I'm going to box that up right there. That's looking great. And let's see, I know there was a part B. And so let's answer this and round this out. So it says, what new average speed should the pilot maintain so that the total time of the trip is 90 minutes? Interesting, okay. So let's see what's going on here. if I remember correctly, so the pilot started here and went for 15 minutes. Everyone okay with that piece? So 15 minutes starting it out, which means the pilot will have 75 minutes to go from here to here. Okay, so the time is going to be 75 minutes. And might want to put that in hours just as I'm thinking of it. And as a matter of fact, we have the distance. That's good. So we've actually solved the whole triangle there. So we have the distance. Here's the way I'm pursuing this, and you let me know. Actually, let me write this a little better up here. So we need the rate, right? We need the speed. And of course, we know distance is rate times time, or rate is distance over time. Oh, I think this is going to be perfect. So I see this as 276 miles. That's the distance that the pilot would have to travel. In time, 75 minutes. You know, if it's okay with you, that would be 1¼ hours. Let's just put it in miles per hour. And I think we have a winner. So went 15 minutes, another 75 in order to get to that 90 right there. So that's where this number came from, everybody. Another 1¼ hours left in order to travel this distance. All right, let's see what we end up getting. Okay, and last piece, 276, everybody, divided by 1.25. Sounds great. So would have to travel about 220.8 miles per hour. All right, so some interesting math there, some problem solving in order to pull that off, but all in relation to an oblique triangle. Had to use law of cosines, and then had an SSA with law of sines. We went smaller one first before getting the larger one. Hey, that's outstanding. Again, just really offered us a good chance to review some things, some great stuff with this. You'll be doing some partner work on some oblique and right triangles, and some good challenging problems with that. As usual, please let me know if you have any questions, and thank you for listening.